Thank you for inviting me. I'm going to talk in English, and my presentations are in English. My name is Cengiz Özkan, and I'm a professor of mechanical engineering at the University of California, Riverside. And I have multiple affiliations in different departments. My lab is interdisciplinary, and I'll show you our areas of expertise. And first of all, I was asked to do an introductory talk and describe what nanotechnology is. And the title of my talk is the Nanotechnology Landscape and Advanced Nanostructured Materials. Okay, so first of all, let's define what nanotechnology is. This is engineering and science conducted at the nanoscale, and please pay attention to this scale. Essentially, 1 nanometer is 10 to the minus 9 meters. So, if you want to get an idea of what this is, so how thick is one hair filament? So that 150 microns. So this is a very exotic world. So things are very small with different properties. The laws of mechanics, as we know, are insufficient. We need much more. And the answer is in quantum mechanics, but we are not going to bore you today with this. So what is important is to understand how to manufacture various things in this length scale. So this is key factor. And in order to manufacture, we have to understand how to characterize. So they have to go hand in hand. And one reason why nanoscale science is still a challenge is this. So we need to be able to characterize. Most of the time, not always, if you say if you cannot see it, you cannot make it. Although there have been examples in the past, Wasson and Crick were able to do DNA research without seeing DNA directly. But most things today, especially if you are looking at things in the more physical sense, we have to be able to see it. So now also bridging this to the industry, is this feasible? So, or is it practical to do whatever you are set to do? So you can build something, basically atom by atom. Is that feasible? Well, the answer is no, but you can make something. Can you build a transistor in this way? Very much possible, but is that sensible? So defining 1 million transistors on a chip, that will not work. We are going to see a number of different people here, engineers, physicists, chemists, and biologists taking place. And you may wonder who first conducted nanoscale work. We may argue on this, but 5000 BC, in ancient Egypt, gold sheet hammering down to about 50 nanometers thick. But of course, they didn't put this name at the time, so they use these sheets to wrap jewelry. Okay, so, but since then, especially the field of chemistry, involved a lot of things at small scales. One has to understand, so we can think about this in terms of two separate tiers. So one is academics and the other one is industry. So they have to go hand in hand if you were to commercialize nanotechnology. So on the left, I'm going to call this the nanoscience. And I'm an academician, and I'm trying to do entrepreneurship. And I have to understand what the industry needs. Similarly, the industry needs to understand what is taking place in academia, and then we need to try to marry those fields of science with actually the different sectors of the industry. So we look at here, starting with physics, and engineering, biology, you have medicine here, and chemistry. So many primary things here. We provide answers, okay, to many problems, and then we actually show the possible route to how things can be applied here, let's say to healthcare. So those people in medicine and biology will have many different ideas. They are going to work together with different fields of engineering and show solutions. Construction, agriculture, textiles, recreation, okay, transportation, etc. So actually, this whole thing is very complex, and I'm very happy to see. So this organization is aiming at merging the two and then finding out various opportunities for products. So this is actually the integration we are seeing, and we would like to see more and more in the future. So if you look at the society with different branches, so one thing, well, there is public perception, there is a media entertainment, so you're going to see news, okay, somehow, okay, so this person has come up with this new nanoparticle, and then, okay, boom, so we have a solution to this, okay, for example, health problem. And then we have economics on one side. Oh, okay, so we look at a lot of the different things. First of all, the feasibility, and then production. Okay, if I have a certain class of nanoparticles, can I produce 1 gram or 10 kilos? What if I need 1 ton? So this was the problem. You're going to see news for within Fortune 500 companies. You're going to see small businesses forming. Investors are very important. We need to bring more and more investors. You're going to see federal funding agencies in the US. We have Department of Energy. We have the defense agencies, NASA, NIST. So this is National Institute for Standards and Technology. So you're going to have different federal opportunities for starting businesses. So these are small business initiative research within the US. Patent laws are very important. So we come up with things in academia, then we come up with various things in academia, and then we would like to work with the industry, and obviously patents are very important. And with that, we look at technology transfer from academia into industry. So there are a lot of different factors, so it's a very complicated and dynamic environment. So we hope to see that the interaction of academia and industry, okay, so merging nanoscience with nanotechnology will have a major impact. Locally, regionally, nationally, and worldwide. So we are just at the onset of this, let's say, wave, and then so it's going to influence how research in academia will take place, okay, within the future. They have to work with actually with the businesses, and also this will also influence how the governments will actually handle the different actions and activities across. Very much my own answer is yes, so we will see, actually we are starting to see the first signs, so it's now the next disruptive technology. So every curve here, as you can see, let's say in the 1770s, here it's about 1850s, so there's steam, electricity, textiles, and automobiles. A telecom over here in the 90s. Over here we have more and more electronics. more multimedia handling, again over here, nano itself. So we are still on the rise of the curve, and we are going to see more and more. This summarizes what we learn from nature, and then actually what we injure ourselves. So as you go down, you look at smaller and smaller dimensions. So here, from larger objects into smaller, down to the molecular scale, and corresponding scale for different objects that we fabricate. So over here, a dust mite, human hair. Over here, the blood cells. This is toxin, neurons. Here, you are going from 12 microns down to 2 or 5 microns. Smaller than that, cellular level. So this is a sort of biological motor over here. If you look at the corresponding scale, so up here, this is an atomic force microscopic tip. This is what we call a multi-scale actually micro nano tool. Gives a long bar. However, the tip is at the nano scale. Chips over here, so this is pretty much 100 micro scale. Down there, at the subcellular level, we talk about carbon nanotube devices. Smaller than that, you look at DNA. DNA is our wonder biological material. 2.5 nanometer diameter corresponds to carbon nanotubes or quantum dots. And we also want to look at this in a way, so if you look at this rightmost column, we look at things that we would like to build from the bottom up. So you look at different nano components, and then we try to arrive at a self-assembled structure. This is a long journey, so we are able to do here, this shows you top-down manufacturing versus bottom-up. You can build physical structures, putting, let's say, xenon atoms on a gold surface with a tool called scanning tunneling microscope one by one. This is a very serial process. It took about, if I believe, at least 24 hours to do this. But the question is, can you build something feasible? The answer is no. So the field of nanoscience will have to explore how this can be manufactured with a parallel process. Quantum dots, perhaps one of the most pronounced nano products out there. We can change the dimensions of cadmium selenide crystals, and then the color will change because the different optical properties emerge. This is porous alumina template, and let's say the pore size here will range from 50 nanometers in diameter down to the smallest pore we can do in our labs about 5 nanometers. This is a very useful material. We can use it as a filter, or we can use it as a template to grow nanowires. Gecko structure. Actually, I have friends in the US who are trying to mimic this with carbon nanotubes and other small fibers. So this actually is key. You can do tactile sensing and actually do some very interesting applications for a very formidable interaction between two surfaces, and there's a lot of defense funding coming in this area. I'll skip this one. Small break. Okay. So application areas are interdisciplinary. So we look at scaling trends in semiconductor devices, we look at scaling trends in sensors and actuators, and in biology and medicine. So this drives the field of nano. And we look at these different needs, and then for example, if you look at the evolution of central processing units, we have to go smaller and smaller sizes in the different components that make up a chip, because that way we can squeeze in more functionality and more power. Bioinorganic interfaces, so this is something new, previously unattainable properties. So you merge those properties with biological materials and then let's say inorganics such as quantum dots or nanoparticles. So we can find out different properties. Most fabrication out there is still what we call conventional top-down fabrication. For example, this is chip fabrication. And this is really transforming into nano. The new concept is if you can build from the bottom up. So putting things together and building larger and complex things. It's important to understand, the need to build a nano toolbox. So this is really what we have in terms of nano components and schemes for fabrication. My own lab has been building different material systems, fabrication procedures, and this takes time to evolve. And it makes sense to work with the industry to be involved. And then you need really, so Zia has explained this, so you need a proper human workforce. So this is in terms of think tanks and get implementation. So every part of the sector will have to have the proper people with the right training. So, and this is key factor. There are many different areas, and how much time I have? Okay. So there are many different areas here. So beginning with nanoelectronics. So this is one of the major driving forces. This really is given by the IC revolution and a miniaturization. So trends in this drives the field of nanopatterning, nanostructures and nanometer complexity motion. So really, the field of MEMS has evolved into NEMS. MEMS stands for microelectromechanical systems, and NEMS, non-electromechanical systems. So these are actuators and cantilevers, etc. But so actually, the need to go to smaller dimensions has made this evolution possible. And you may come across this name called nanolithography. So this is something we use almost on a daily basis. So this is basically patterning you do at the nanoscale, and this is something that directly comes into play. Sub-nano. So going beyond nano is atomically controlled nanostructures. So actually we are within academia, we are already going beyond nano, and this is basically going to less than 1 nanometer size, and this drives because you look at different properties and different functionalities of materials and devices. Chemical approaches are very important. There are many different things here. I'm not going to bore you with the different details, but essentially synthesis is key factor to achieve nano and sub-nano materials. Especially nanotechnology in carbon. I'm going to explain a little bit more today. Fullerenes, nanotubes, they are very important. Self-assembly and self-assembled structures. So this is building from the bottom up. Manipulation. So we can move things around. We can use, for example, something called optical tweezers. Maybe people in the industry won't know this too much, but we can use this light. So this laser light itself, it's about 5 milliwatts of power. And I can focus this with a lens, and I can move live cells or small particles. Nanoscale magnetic materials. There are many different opportunities there, especially for hard disk industry. And then nanoscale imaging is also very important. So let me tell you about my lab. So my group spans to 4 specialized labs, and we have about 4,000 square feet space. Current number of doctoral students there, 20. So these are really so this is a high caliber workforce, and they are trained in many different areas: biology, chemistry, and engineering. So far, we graduated 28 PhDs and 50 masters, and we raised about $10 million in funding. This sort of outlines some potpourri highlights, and then so this sort of summarizes the portfolio of nanomaterials and different technologies we have. Here range from what we call nanowires, nanotubes, blood copolymers, single layer or multi-layer graphene, 3D forms of carbon and silicon. Over here, bio-inspired materials and systems. We can use viruses, we can use DNA, and then over here, different applications. At the intersections, shown by green, we have biochemical sensors that make use of the different properties, memory and electronics over here, and then also energy storage. We have advanced technologies in batteries and supercapacitors. Over here, nanowire sensors, different interconnects, solar cells, and one late area in our lab is spintronics. And these are various examples. So just to show you how interesting this field can be. So you may wonder what this is. So this was published in Nature, one of the highest formidable journals in this area. So this is the core of a virus. So this is a DNA or RNA, and right in the center. And around this cylinder, which is the outer shell of a virus, we put metallic particles. This is enclosed into contacts. And then when you apply a bias voltage, you can induce a charge to be stored within one of these particles. So this was the first virus-based memory device. Many different things over here. We have nanowires. Over here, you have a device made out of nanowires. These are viruses, plant viruses that form actually the cluster. Over here, schematic representation of plant viruses with different attachment sites. So we can place different points on a virus. We would love to teach the people in industry these things so that they can come up with different applications. So this is a very special interest for us these days. The graphene is the wonder material. So this is an authentic two-dimensional hexagonal lattice packed in this what we call a honeycomb structure. So this sheet can be rolled into carbon nanotubes actually. So or buckyballs. Carbon-carbon bond length. Okay, so these are some interesting numbers, about 0.14 nanometers. So we are already talking about the atomic scale. And then you can have different shapes piling up, just making a piece of charcoal. The separation between each layer is 0.34 nanometers. Again, basis for fullerenes and carbon nanotubes. So going back here, my lab is specialized in actually building these materials. We have different technologies that can actually use these materials. What we call chemical vapor deposition growth is very important. and we can have 2D and 3D forms of materials. Something else from my lab. So this is a different capability, and actually this is a lab scale, almost semi-industrial. So the industry has these machines that can fill up this room. So this is a smaller scale. So it's called a metal organic chemical vapor deposition system. So such machines give you the capability to grow different atomic layers. And with this machine, our interest is to grow these two different types of materials. So this is called molybdenum selenide and tungsten selenide. You may wonder why these materials are important, because, for example, you have a similar material. So you have a similar material that you use as a lubricant, and we use this for different applications, and especially for the field of electronics and skin products. I would like to take up just a couple more minutes because I was asked to do a different presentation as well.
Farklı bir sunum yapmamı istemişti.
Yes. So after giving you the highlights of what nano is from the academic perspective, I'm going to take just a few more minutes to show you real products out there.
Ürünler hakkında bilgi vermek istiyorum.
Textiles. So how can nanotechnology enhance textiles? So Levi Dockers, coat pantolon. So they actually use nanoscale Teflon fibers interwoven into fiber of pants. You pour something accidentally, so it has hydrophobic properties that actually repel the liquid. Bu şekilde bir şey döküldüğünde bunun kirlenmesini engelliyoruz. So this is basically what they advertise. You can buy these things online, and this is termed under nano dry. So this is a nanotech innovation. Moisture wicking retains breathability of fabric and quick drying. Sportswear. So New Balance is a very famous company out there. So they found a way to fabricate nanoscale channels that redirect moisture away from the body. So for example, I'm sweating now, but they have fabrics out there that will actually help channel moisture out. Winter wear, so this is called stain-free clothing. This is what we call nano whiskers, about 10 nanometers long, made of a few atoms of carbon. You can resist spills, stains, resist static, and coolest comfort. So this is reality. So these are out there. Odorless socks. This is antibacterial, odorless product. Uniforms, textile uniforms, police uniforms by the company called Albeco, again, Nano Dry. Nano ties. So you may buy one. So essentially this is a high-tech fabric, and they repel water gangrenes. Let me show you a couple more. So, well, this is very famous. This has been out there for a long time for sunscreen. So, güneş krem. So you use nanoscale zinc oxide particles in here. They screen UV, and you apply it as an invisible cream. Let me see. There are many other examples here. Nano and UV artificial tooth cleaner. So you use nano silver particles, remove debris on dentures. Products for tennis. So tennis balls, the inner core coated with a nano composite coating
Topun
basically
merkezinde
inhibits permeation of air from
nanokomposit,
inside.
kaplama.
And let me find just one other interesting one, and then I'll stop right there. Okay, so it's just right there. So tennis racket. So one of the best in the field. So they use carbon nanotube reinforced composites, makes it lighter, more exciting, and more power with a lighter weight. So I'm going to stop right here. I've spoken enough, but örneklerden aslında bu tür şeylerden çok var. Özellikle nanokompozitler. Polimerlerle nanopartiküllerin, nanofiberların bir arada bakılması çok popüler. Yani buna biz de bakıyoruz. Karbon nanotüplerle, buckyballarla. Değişik bir sürü nanopartikül var. Bunları değişik polimerlerle de deniyoruz. 10 dakika falan önce bahsettiğim bu black polimerler var. Bunlar yepyeni polimerler. Değişik özellikleri var. Yani bunlarla ilgili çok daha detaylı konuşabiliriz. Thank you very much, and I'll be happy to answer any questions offline as well.